Bloop. So let's get started. And I do have Desmos up to remind me that we need to do that every time. Every time we need to do that. And that's a good thing. That's a good thing here. Except for the fact that I can't put it all on one page. So I am going to do this. Sorry, but you're going to remind me now, and it'll be great fun. Oh, yeah. Yeah, I need to do that as a reminder. Yeah, Desmos. Every time Desmos. But we do need to set it up. We do need to see what's going on. And I need a refresher on what to do here because I'm kind of lost. The ones we had done last time, they basically gave us the formula. It says find the flux, find the circulation. We went back and we looked at it. Today I was stuck because it says find the amount of work. Okay, well that's different. It didn't ask for work yet. So let's go back up and reread everything we got. I'm looking for the word work. Mm-hmm. Uh-huh. Yep. Looking for the word work. Yep, don't see it. Nope, don't see it anywhere. Those are your two big paragraphs. I don't see work anywhere.
I have a question. It said counterclockwise. I didn't see that down in the question.
Oh, did it?
Yeah,
Well,
counterclockwise.
well, everything's counterclockwise. Didn't we have a discussion about that in college algebra?
I took 13, 14 for college algebra.
So the entire universe is counterclockwise. Except for clocks. The clocks are the only things that don't do that. So this is just saying in a normal universe. Okay, now that we established that much, so we need to know what it means to have work. And I'll just have to tell you because it took me a while. It's the FDR. At least I believe so. So this is what they're looking for. Well, let me go find that now. Because now I have to go back up and see what formula that is. So looking around and I don't see FDR anywhere. It's technically between these two guys. And I'm telling you, as you probably wrote down last time, it's this one that's the FDR. It's that guy. So essentially, I'm like skipping all this and going immediately to the end. That's my goal today. So, and thus, I would say this is also work. So if they have to do work, that's my work formula. Is that one? Cool. So that's my formula. I'm going to toss it in, use some Desmos, and be done with this. That's the goal. So let me rewrite what we're actually doing. Double integral of, I think it was n sub x minus m sub y dy dx, essentially. Like dA, whatever we're going to use here in this case. And so let's get the inside, because we can do that. Again, this is my m, this is my n. And I want to write it funny for just a minute. I don't know if you like this format or not. You probably don't, but, well, just exploring your brain a little bit. It's this sub x minus this chunk sub y. So those are derivatives. Are y'all okay with my notation a little bit? It says fx, essentially, right? F sub x. Derivative in terms of x. But just has stuff there, I guess. So what would be my derivative in terms of x? Yep. Perfect. Yep, that's right. Minus sign. Now in terms of y, would it be a 9? But you're right, though. That's good. Bloop. And then I'm going to do dy dx, probably. I haven't really looked at what's going on here, but that's my general go-to, you know. I want to fill in the limits. So, looks good so far. It says first quadrant enclosed by x-axis, x equals 1, and then x cubed. So let's draw a nice picture here. So x-axis is this guy. Oh, you know what? Yeah, that's fine. X equals 1 is going to be this guy. And then x cubed would look kind of like this. Kind of does that. So, little zone in here, right? The little zone in there. Let me do a different color because it looks cool. Yay! Yes. Oh yeah. Oh, you're right because they're the same. Oh, I didn't notice that when I was doing that this morning. 5? Is it a 5? Okay. I didn't notice that actually. Thank you for that. Okay. Moving on though. Very good. Very good. So I need to find my limits for this guy. I need to find an area basically. So we have a top. We have a bottom. What would I put for the top? Yeah, x cubed. You got it. And then the bottom? 0. And then we got left side. And we got right side. Where we go for x? From what? Perfect. 0 to 1. You got it. So I toss a 5 in the front. In it. Ah! I was going to see how far I got before he said something. You're right. Yeah, Desmos time. Let me do this. I think that'll fit practically everything. So yeah, exactly. Thank you for reminding me. I was just gonna, creep along, see how long it took. And there you go. We're done. And that is the answer. I'll flash the answer here in a second. I just done this a couple minutes ago. So yeah, flash the answer. There you go. We're good. Cool, right? Fun times? Fun times in math class. Okay. Any questions though? It almost went too fast. Like I actually wanted to slow down and have more fun with it. But then you said Desmos, and well, there it is. We're done. True. True. Yeah. Yeah. Good. 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 Okay. Good. Okay. Cool. I'm gonna scroll on then. Yeah, it's fun. So find the work done. We already know what the work would be, so that's my integral FDR business. And I have an F, and then I have not an R, kind of. Right? We could do this old school, or we could do this new school. I don't know. So here's the thing. We have the FDR, or we could do double integral of the, help me again, NXMY dA. So either way is fine. Well, if we're doing it with the area, what does the area look like? It's a circle. Where is the center of the circle? 2, 2. And what's my radius of the circle? Yeah. Yep. So it's like this, basically, something like that. That's my area. That's my area. So I would have to integrate over this area. Y'all don't see it online, but I'm sitting down. That's the sit down moment, right? Do you want to integrate that? But we have a variable density. That's the problem. I mean, I'm assuming a variable density. I haven't done the math yet on it. It might. You know what? It might be that. But I'm not going to assume that right now. Okay. Let's say I have a variable density. What's up? Oh yeah. Oh hi. I don't know. Is it? Yeah, I know. So that's if you're gonna guess, 0 is a great guess. Are you gonna guess? Did you want to try to do an integral for that circle? I'm doing a sit down because it's a concept here. Do you like integrating a circle? Are you thinking rectangularly? What about polar form? Would it? That's the problem. So, because it's not centered at 0, polar form would actually not be happy at all. Because I don't know how to describe this in polar with it not being at the center. Rectangular, I'd have to do 2 separate integrals. And you can't assume that the top is the same as the bottom, therefore I could just double it or something. No, I can't assume that right now. So you can see the predicament we're in, right? So here I'm going to ask, should we try to find an area, or should we use basically blah, blah, blah dt and just go around in a circle, probably ending in 0? I'm gonna try this. So let's go back. This is old school, as in like last section essentially. I want to do this for this particular problem. I just want to try it. And so the formula is f dot r prime and then dt. Okay, so that's what we need. We need an r, and then we need an r prime, and then we can dot product it and all that stuff. So then I need to find an r, a vector. It's 2-dimensional. It's not too bad. How can I find? And it looks like radius, but it's not quite. It's just a path. Can I make a path for these kind of guys? So normally a circle going around, wouldn't I just say x is equal to cosine and y is equal to sine? Right? That's easy, but it's not quite centered at 0 now, is it? Can I just take these and shift them somehow? How? There you go. I'm saying if x equals that, I'm now going to shift it by 2. So I'm technically just doing whatever I had plus 2. I know that sounds kind of weird. It's like it was over here. Remember x minus 2? But now I'm like shifting it to the other side. So x would equal cosine plus 2. I'm saying x is normally equal to 2, but then I have cosine kind of variant from it, varying it a little bit. And the same with the y. It would be a plus 2 as well. But I still don't have the full encapsulation here. It's getting closer. I'm missing something. I'm missing something small. There you go, the radius. Yep, the radius is 2. So here's my hypothesis, okay? Here's my hypothesis. Oops, shouldn't have gotten rid of that one. My hypothesis is that x is equal to 2 cosine t. That's my normal circle, but I'm shifting it by 2. Same with the y, 2 sine of t, but I'm shifting it by 2. And eventually, I'm going to go 0 to 2 pi for my integral, and everything will be happy. How can I test that? Starts with a D. Oh, yeah. So what we need to get familiar with is testing stuff out. Does this look right? Is it working okay? Let's try it. So I want to just try this formula that I kind of made up. Does that even look good? Is this what's going to actually make it look pretty? So I do x equals this, and then I got y equals that, and you can see it's not good. Something's bad. It's not working right. How do you make it work in Desmos? That's exactly what I was hoping for. So, stunned. And that's fine. You're not supposed to be experts at this. But hopefully I'm not either. I'm not expected to be an expert either, I hope. Okay, I know that looks a little silly, but what we did, let me do this a little bit, is I put it in parentheses with a comma, and it says we want to go 0 to 2 pi. And you can see we got a circle. And if I scroll in a little bit, I'm centered at 2, comma 2, and I have a 2 radius. So I did get what I wanted. So I'm creating a path formula from nothing, and it's a little weird. You do not need to do this. There's other ways to do this problem. I'm choosing this way because I think it's going to be easier than the other way. Because again, finding the area of that would not be as easy for me. Yeah? Okay. So now let's try to put it all together. So I'm basically, I've proved that this is a cool set of, I don't know, path thingies. I can essentially now say this is 2 cosine t plus 2, and this is 2 sine t plus 2. And now I need to find r prime. Like, that's not part of the problem, you know? What's my derivative in terms of t here?
Wouldn't that be two sine?
Yep, yep. Very good. And the 2 goes away. And this guy?
That'd be just two cosine.
Yep, sure. All right, I'm going to now take this. I'm going to dot product with this guy, basically, and we're good. Except, you see there's another problem here? Like if I take this and I dot product with that, I'm mixing up my variables. I need to have x equal to this stuff here. And so, yeah, this is going to get a little on the weedy side for just a second, okay? Let me replace this with t's. So then I've got 3 times 2 cosine of t plus 2 minus 2 sine of t plus 2, comma, I'm just doing this one right now, x again, 2 cosine of t plus 2 minus 3 times 2 sine of t plus 2. So again, that was a x, that was a y, that was an x, that was a y. Dot, I'm running out of room, this thing right here, dt, 0 to 2 pi, hopefully it works. And I hope so. I don't really know, because just to be honest, I didn't do this before class. So I'm a little nervous, but I think we can get this done. The dot product is a very simple process, though, right? I'm just wanting to say this chunk times this chunk. This chunk times this chunk, right? Just a dot product. Add them together, see what we get. So in the end, oh my goodness, there's so much going on. Do you want to like simplify and distribute a little bit now or not? What do you want to do? Simplify or just put it all into Desmos? Well, yeah, it's just going to be messy and long. I'm voting to simplify a little bit. Okay, so yeah, let's do the 3 I'm going to distribute, and the minus sign I'm going to distribute. And so, and then I'm going to also multiply it by this thing. So negative 2 sine of t times, I got 6 cosine plus 6 minus 2 sine minus 2. So that's the first part. And then I'm going to say plus the 2 cosine of t times, now I'm going to simplify that a little bit. So distribute 2 cosine of t plus 2 minus 6 sine of t minus 6 dt. I'm going to change colors. I don't like that so much anymore. So I distributed here, and I'm still multiplying these guys in the front. You can see that those right here are the other guys. But then I want to distribute those. I think I can combine like terms a little bit. Now, they look like some of these are going to be the same and they might cancel, but it's not quite ready for that. Almost. Distribute. Remember for like how many years they said, no, you got to simplify. And then Chad comes in and says, no, man, you don't have to simplify. And then actually, yeah, you do. So, man, Chad's so mean. Lying to us. What a bad teacher. Oh, never mind. No. I'm the world's best. No. That's kind of funny. I think that's going to be a sine squared. A lot of this, I'm hoping, will either cancel or something. That's going to be a cosine squared on this side. 8 cosine, and then I've got a 12 cosine sine. Okay. And I'm verifying the SIGN signs. So these guys here, they don't cancel, but they kind of combine together. What would I get out of these two right here?
Couldn't you get factor on the 4 and then turn to a 1?
Yeah. 4. Just 4, right? These guys here would just be a 4. Because they both have a radius of 4, essentially. You're pulling a 4 out first. Yeah, I like that. And then these will combine to make a 24. So negative 24. Although I hope that they canceled. It didn't seem like they did. And then we just got the other two guys hanging out. Remember that plus 4. Don't let it go. And there we go. I'm going to now go to Desmos finally. Chirp. And okay. And 0 to 2 pi. Okay. I don't know what the answer is for this one, so we're going to find out. It might actually be 0, and that would be really funny. Not 0. Not 0. Close enough, right? You're only off by 25.132. Correct. That's probably another thing that we're going to need to do. So if I divide it by pi, oh, look at that beautiful number. So yeah. Now let's go and check the answer. I want to go check it, and yeah, sure enough, it's it. We did it. So, oh please, yeah. So yeah, now that you see what's going on, that's the whole chunk of it. Sine t 8 sine t 8 cosine. That's a. Oh yeah, sorry. There's a t there. You're right. It's sine of cosine. Yeah. There's a lot of moving parts. Since we have a little bit of time, I want to see if maybe the Green's theorem stuff is better here. Did I say Green? It is Green's theorem we're on, right? Okay. Okay, good. So I want to see if that area formula, the Green's theorem stuff, will be a little better, maybe. But my scaredness, my fear is in the area part, right? Let's just see, though. I have an idea. For this problem, not every problem, but this problem, there might be a better way. Y'all just tell me when you're ready. No rush at all. But you get the concept, though? We're doing the FDR. The main hiccup would be, what was the path? We had to create the path. Good thing that we have Desmos to double check ourselves, right? It's just not perfect. So how would we do this in this format? Without going too deep, I want to just see what the inside's going to be, because my claim was that it was tough because the variable density of the area, right? Well, funny how this works. This is n, this is m. What's my derivative in terms of x? Minus derivative in terms of y. Okay. So what you just found was that there's a 2 in there. You're saying double integral of 2. You're wanting the area times 2. The area of a circle times 2. So 2 times pi r squared. What was the radius again? 2. Done. You cannot guarantee that. You cannot guarantee that every time. We have to have a backup plan. Okay? I know. And I didn't want to lead it on. Like, oh yeah, you're right. Area of a circle, done. But we have to have a backup plan just in case. It was very simple this time. But what if they had thrown something else up there? What if these were not linear, but there was like an x squared? Whole thing's blown. Have to do something else. Cool? Oh, yeah, no problem at all. I'll even put a little dot here so I feel like I did something. Yay! Yeah, it's silly, I know, but on this problem on the homework, should be fine. So good thoughts, though, on, hey, we know the area of a circle, right? That's actually a great thought. Right, which was easy. Good, good. Cool? Cool? I know it's almost like frustrating. Like, you made me do all this problem, but it's just that. I'm just trying to prove that there's like, there's a just in case. We need to be just in case, need to be ready. Okay. Change my color. And when you're ready, I'm ready. No rush at all. Happy times. Cool. Scrolling on. So, it just says do it. And I love when it just says do it. But before we can, I need to look at what the formula is, okay? Can we just do this? Probably. But then I need to do the path thing, and if it's in rectangular, it's really hard. So I don't want to go down that road too far, okay? Maybe there's an easier way. Like it says, greens. What is this formula? What is this form? So let's go up, and I'm looking for this on a previous page. And basically, it comes down to which one of these is it? The top or the bottom one? So one more time. So this is what we have. We're looking right here, and I'm saying which of these is it, the top or the bottom one? Top or the bottom one? Which one's better? Top, right here. That's exactly what it is. Yep. That's what we're looking at. And what's the key indicator? Yeah, the dx in the right place, the plus. Yep. The dx plus the dy rather than dy minus dx. Yes, yes, yes. All of that is perfect. Very good. So we're using the top, which means that I can say, oh, well, I know this formula. Greens, right? That's what we're going to do, is the nx minus my dA, just like we did last time. Copy paste of what we just did. And you're going to be, if I do this the long way, you're going to yell at me again. So I'm going to do it the short way, which is good. It's good. So this was m, this is n. So what's my derivative in terms of x? Just a 7. And minus this one. Thank you. So now I have a double integral of 5 dA. It's wanting 5 times the area. And oh, look, it's a circle. Oh, look how nice. Regardless of it being shifted, what would be the radius of the circle? What's my radius? Very good. So then I have 5 times pi square root of 2 squared (10 pi). We're done. Let me verify. I'm just going to flash the answer, and there it is. Very good. Look how fast that was. So it's just like the last problem, but I did what it said. I didn't just go off and do my own thing for a while. Cool, right? It makes it super easy. We like these. It's not always that way. But at least here, it's kind of nice to see once in a while. Yes, exactly. And that's fine. And if it didn't, we would do our own little thing. Like, it would be a little weird here. That's fine. We'd create a formula and make it work somehow. Cool? Yay! I love when it's easy. Okay, this is the one I did this one before class, and I got it wrong, finger quote. So what we need to do is a little bit of Desmos beforehand, because what they're talking about here is blah, 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 use the formula and get it done. Great, but it says one arc of this and that, and I don't even know what that looks like. So we need to use Desmos just to kind of give it a view, yeah? And we can do this now. We can do Desmos graphing. So my goal right now is to graph this and see what we can come up with. Notice again that I'm using the parentheses and all that stuff. And then I'm going to go from 0, probably like to pi or 2 pi or something. I don't know. So we got that. 2 pi. Okay. Thank you. I thought it looked different than what I had done earlier. I was like, that looks a little weird. Okay. 0 to 2 pi. Looks like, and it says 1 arc and the x-axis. So like it looks like this little stuff is what we're looking at. We're wanting to go 0 to 2 pi, I guess, whenever we do some math here in a minute. Okay? So that's our picture. Okay, awesome. So back we go. It says apply this formula. Go, figure it out. Okay, so we got 1/2 of integral something x dy minus y dx. I don't even have a dt. I don't know what to do. What should I be doing at this point? Like we found the picture. I think the picture looked really cool, right? It did that, and that's at 2 pi for time and blah, blah, blah. But what do we do now? This is that leap right here. Huh? Come on. Tell me what you're thinking. Is that a hand up? Or are you touching your ear? Oh, hi, yes. Yeah, what's up, bro? Yeah. You can just call it. There you go. We have an x, find dx. We have a y, find dy. Once we have all these, what do we do with them? There it is. Copy paste. When it says x, you put an x. You put this x. When it says dy, you put dy. Whatever we get here, boom, plug it right in. Yes. That was the key. That was the little trick. So yeah, what's my derivative of negative cosine? Positive sign derivative? Positive sign from negative cosine, right? Derivative. Okay. No. Hold on. Hold on. We always got to redo the chain thing so we can see, right? So this is derivatives. And so I'm right here, and I actually came all the way back up, right? That was my derivative side. Okay. I did do this a couple minutes ago. Okay, so then negative sign turns into negative cosine. But this one has a small extra right there. It has a 5. When I did it the first time, I got it wrong because I forgot the 5. I forgot the 5 right there. The whole thing was wrong, so yeah, watch out for those little dudes there. DT, technically, but I think I wrote too tiny. I'm so sorry. Yeah. Okay, we'll figure it out. So I'm going to start plugging it in, substitute, exactly. So my x, I am literally copying down whatever was an x. And then it says dy. Fine, I got a dy. Minus sign. Y. Oh, about to mess up there. And then dx. I'm going to get rid of my chain, sorry. It's kind of getting in my way now. dt. They both had a dt. And we discovered from Desmos, we need to go from 0 to, 2 pi. Pop it all in and hope for the best. Here we go. I'm going to expand it, sorry. There we go. All right. And the 1/2 in the front is important. Isn't Desmos so nice? You would have had to do that by hand. Sine cosine thing, yeah. Yeah. And this guy would have a square, I believe. Are these, hold on, did I do this right? Are these the same? I think so. That's weird. Okay. What did I do wrong? Okay, that's not what I was hoping for. That's better. So we got a negative 75 pi, essentially, which is totally wrong. It's a positive 75 pi. Yay! I'll flash the answer to prove it to you. There you go. Yeah, that sounds great. Sounds great, bro. I love it. Yeah, I'm not exactly sure. It might have been something to do with my arc. I don't know. I wonder though what if I did 0 and negative 2 pi. Oh, same thing. Okay. Right here?
Yeah.
Oh, yeah. I mean, but that's not correct. Yeah, so I don't know. Not sure, but yeah, it's because it's area. I don't know.
Depending on the unit, since it's inches square, like if it's inches square, you know it's gonna be square, therefore it's positive.
Yeah. Have you taken like Rabani's physics class?
No.
Oh, well then you'd be great at it.
Okay.
Volume can be negative, okay? According to James.
Exactly. Show me a negative volume in a vacuum chamber. You suck out all the air. Does it have the same amount of air as the outside? No, it has less than, so therefore it's negative volume.
Man, if only math were that easy. So here's a thing. I want to stop and pause and talk for a second. I want to zoom out. We got 16.5, which is difficult. It's not terrible. It's just really weird. Like, look, come on, pick which one was right. You know what I mean? And then go ahead and create your own now. These are not as easy, and we'll get through it. Surface integrals, kind of a continuation of the last one. So that's it. One more. See, it's the same formula from the other one. Scroll on, scroll on. Stokes. We're getting really close to the end of the course now. This is just a formula. It's trying to simplify things. This is the true curl formula. We just hadn't talked about it, but you can see the FDR is still there. Last is divergence theorem, and then we're done. So we're really, really close. 4 sections left, right? Do we have 4 days left? No. Okay. So you know what would be awesome is if we did some homework, right? And what I would like for y'all, now that's the end right there. What I'd like from y'all is to tell me what homework you want me to do. Like now. So we've got 15 minutes. Yeah. Oh. Have we not done that?
No, you wanted to wait for everyone else to get here.
Dang, it was supposed to be today then, but we don't have that. Are y'all all going to be here tomorrow? Yeah. Okay, then let's plan on it tomorrow. You're going to remind me. You will remind me. Yeah, to do the lab tomorrow, which is fine. I'm okay with that. Please tell me. Yes. I would love to do it. One of the hard things with due dates in particular, and this applies to both us here in the pilot and also later kind of things. You see, like I pushed the due date back on chapter 15. Sounds awesome, but then like if you're not working on it all the time, it kind of catches up, you know? Yeah. 15 what? 15 15.5, question 11. Okay. It's tough because see how I'm getting close to done with chapter 16, but here in the homework I'm in the middle of 15. Not bad, but it just makes me scared for y'all. So and I'm here for you. We can do homework for a week or two. I wouldn't mind. But oh yeah, this is fun. I love doing this. This is one of my favorites ever, and I got to tell you, there's a reasoning behind it. I have this technique for it. It's called dimensional reduction. That's what I call it. I don't know what other people would. Let me show you. It's a really cool problem. You know what's so funny though is that I saw it and I'm like, oh yeah, this is cool immediately, and y'all are like, but Chad. And I even told you the technique I'm going to use. Like, it's that fun and interesting to me. We're trying to find the volume. What I want to do is I want to look at it from a couple views. We already see the 3D view, so I don't have to redraw it. But I want to do a 2D view and then a 1D view, okay? So let's go with the 2D since we're already seeing the 3D. So this will be 2D, X and Y. If I had to look at this from the top, looking down, straight down, I want to look at what its shadow would look like. What would it look like here in 2 dimensions on the XY plane? Just give me a name. A triangle. Very good. It would be a triangle. If you're looking here at X's and Y's, I think it would be 2 X's and 1 Y, because this guy here is at 2 and this one's at a 1. Okay, so that's the 2D version of it. Right? When I'm looking at it from the top, straight down, what would it look like if it had a shadow? Awesome. Now I want to do the 1D version, which I can't even draw it like that. That was incorrect just to start with. A 1D version is very strange. It's only X. I can't even do 1D. It just makes me feel weird. I'm doing this on purpose because I think it's funny. What numbers do we go to on X alone? Perfect. That's exactly right. It would be kind of like a thicker spot right there, I guess. Okay. What we're doing is creating kind of like a way to do our triple integral, because of course volume is going to be a triple integral of 1 dv, but in our case, because it's all rectangular, it'll be dz, dy, dx. Okay. This is my thoughts on this process. What I now need right now, I need z's. Z equals blah. I need x and y equal blah. So my goal now is to fill in all the stuff, in particular right here. Okay, this means this is z equals. Z equals. I need right here this plane to be z equals blah 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 with x's and y's in there. How do we do that? It's back in the day, and I meant like in this class. It's been a month or two. Close. We're getting there. That we will have that in the formula, but it's a much bigger formula. I love this. I don't want to keep y'all in suspense, but see, this is a line, but if I go to 3D, my line is actually a plane. We have the plane equation. And so to get z, it's a little weird. We'll have to kind of manipulate it a little bit. But my basic plane equation looks like that's a c. And then we basically just say, move this over, divide by the c, and we got a z equals blah, 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 right? So it's a plane equation. How do we find the slopes of our plane equation? The slopes of the plane? I say slopes. If you were taking exam 1 again, you would fail. It's the normal vector. It's the normal vector. And how do we get the normal vector? Do you remember? We're going to plug stuff in. It's going to be some numbers. But ultimately, we need to do something with 2 vectors. What goes in between them? It's a cross. Thank you. cross product. We're going to have to do a cross product of two vectors. And then that'll give us that normal vector, which is the slopes. Pop, 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 and we're going to be done. So this will be super fun. But now I'm left wondering, like, what goes here and here, right? We have to create them. So looking at this, I wish I could draw on top, but it's like this vector right here and this vector right here. I love those. Those are two really nice vectors. Two vectors, cross, we're going to be out of here. So I don't know, vector 1. I need to do terminal minus initial for every single one of these little individuals. So let's do this, the z and the x. Okay. So terminal minus initial. What would I go for my x's? Perfect. 2 to 0, right? Because we're looking at those two numbers. So the next one would be and then finally 2 to, yep, -1. Very good. 0 minus 1 is -1. Excellent, excellent. Terminal minus initial going from here to the z. What do I have for my y's, or for my x's now? 0, very good. For my y's. And then finally, yes. Cross, here we go. So always a 0. And hold on, pause for a second here. Is this exam 2 stuff? Is this exam 2 or exam 3? Can we use Desmos on this? So I can't use Desmos? No. 0, we got 2, and I think that's going to be a regular K. -2, -J. Yeah, y'all keep me straight here. 0, always a 0. 0 in this case. 0 this time. -1 times -I? Okay. I'll trust you guys. So 1, 2, 2. So this is my normal vector. This is my slopes. I know we have to go through this crazy long process just to kind of get started, but once we have it, it's a cool little integral and we just get it done. So I'm going to pause on that because I'm going to have to start erasing or doing other things here in a moment. I just want to make sure you're good, good, good. Okay, so I'm going to take those and go way back up to the top essentially. So I have my normal vector was, remind me, 1, 2, 2? Yes. Okay, so then my plane equation should then be 1 x minus something, okay, and I got 2 y minus something, 2 z minus something is equal to 0. Now these are my x naught, y naught, z naught. It's just a point on the plane. You get to pick any point you like. Would you like this one? Is that a fun little point? Yeah. I mean, it has most zeros, and it makes my z just a 1. I like it. It's my favorite. Simplifying. X, 2y, 2z minus 2 is equal to 0, because I distribute. To solve for z, and we get 2 minus x minus 2y all over 2. Okay, I like that better. And that's basically my plane equation, but in a nice, easy form, which I'll use here for my integrals here in a second. So I'm definitely pausing here again. There's another good pause moment. Yeah, we've already had to spend like 10 minutes just to get the plane equation. We haven't even set up the integral yet, but it's okay because that's sometimes how it works, you know. And that's okay. If you had Desmos, I'm thinking it might go faster. There are ways we can make this better, but we'll try that another day. Okay, so now we finally do our triple integral of, again, just 1 dz, dy, dx. And so what would be the bottom of my z's? Yes. What's the bottom of my y's? The same for x. So we got that much. This is part of that dimensional reduction thing that I was saying earlier. First, this is a z equals. So we're just going to put, I'm going to have to get a little bit of room here, okay? So forgive me for my my silliness. I'm going to write it kind of sideways for a second. Kind of hard break it there. Okay, so I got z equals right there. What I want to do is eliminate z entirely. In a way, I'm saying set z equal to 0, go back and solve, so that we can go to 2 dimensions now. And that was going back to my my 2-dimensional triangle thingy. It's the same form. It's the same formula. It's just now I say, get rid of my z. Repeat the process. So now I'm not moving both of these over. I'm moving only the x over and the 2 over. So now I have y would be equal to 2 minus x, and then still divide by 2. You know what's interesting is that this looks very similar to what we had right here. Yeah. Lastly, I want to figure out, and I know you can just see it, but I want to figure out what it would be for x. So what I do now is I eliminate the y. Solve for x. Exactly. What we're doing, and it doesn't show super well right here, but you can basically see I've taken the same thing and I've removed one of my letters every time. And I'm like reducing it down closer and closer and closer. It's way cooler with like squares and stuff, because like you have 3 squares, you have 2 squares, you have 1 square, and it just looks so pretty. Dimensional reduction stuff, but it's the same concept here. Desmos? I know I'm not supposed to, but you want to know if you're right, yeah? You want to know if you've been doing this right for the past 30 minutes. So, here we go. Yeah, this is like one of my favorite kinds of problems. And if you don't like it, then I'm sorry. You're just like, I hate you, Chad. I hate you, Chad. I hate you, Chad. All of that for a third? That's it? Not even a pie? Rampage. No, I'm playing. That would have been so funny. Yeah. Okay, cool. I can recap if you want. I am. Yes? That's an. You were saying yes. Did you want me to recap? Oh, okay. Did you want me to recap? Yes? I can. You're good? You're okay. Yeah. Create a plane equation, and then solve for your z equals. And then, like I said, like eliminate that z. Solve for y. Eliminate the y. Solve for x. That's how I got these guys at the top. Good? Good? Give me another one. Well, actually, don't, because it's only 3 minutes. So, we're going to do the lab next, tomorrow. And I'm okay with doing some homework first. You know, y'all come up with homework and we'll do it. If you don't have anything, I have to keep going. So, you don't want me to keep going, do you? You want me to do some homework, right? I'm like, hint, hint, wink, wink.